Welcome everyone to this workshop. I first would like to really thank you all for joining and taking the time to be here today. If some of you registered to attend this workshop back in January, I'm really sorry that you had to cancel last time. Obviously, I think the lockdown number 3 kind of threw a little bit more in terms of the logistics and running it. But really thank you for coming again and registering again to attend this workshop today. I would also like to thank Chris Maynard for helping putting together the workshop and bouncing idea and how we could be running it, and also obviously for presenting as well. I'd like to thank the two other presenters today, Jacob Tollimson and Pata Meji, that are going to talk to us a bit later about their work. I'm going to do a little bit of housekeeping. Obviously, we're now all very familiar about these online meetings, but just in case, I really appreciate if you could keep your microphone on mute and your video off, because that'll make it a lot easier for everybody, depending on your broadband or where you are. And make it, much nicer explain for everyone. If you could put your question in the chat, that'd be really good. I'll be monitoring it throughout, and I'll ask the question either at the end of each presentation or in the Q&A at the end of the session. The meeting will be recorded. So if you would like anything edited out or your partition being removed, please do email Luis Martinez at the RSS, and she will make sure that your participation is edited out. A little bit of background to start with about the RSS, in case you're not familiar with the Royal Statistical Society. It's a charitable organization advocating the importance of statistics and data. It was founded in 1834 and has over 10,000 members across the world. They organize events such like this one throughout the year, as well as running high-quality training course in statistics and also in coding, so R and Python. I think there's a really good Python course at the moment being advertised. They also organize an annual conference in September each year, and I would warmly recommend anyone interested to kind of check out their website and do look out at the lineup for the conference this year. There are some amazing keynote speakers and very good sessions already confirmed. The workshop today is organized by the Computational Statistics and Machine Learning section, which is one of the dedicated sections of the RSS. The CSML section supports interest in all aspects of the use of computational science and technology in modern statistical analysis. It's also interested in the methodological development of statistical and machine learning algorithms. If you're interested in taking part or volunteering and helping in any aspect of the RSS or this section in particular, do again go onto the website. There are contact details to join. Why this workshop? So I thought I'll start by reminding one of the International Statistics of the Year 2020 that the RSS put together, because I thought it's quite telling. Obviously, with the pandemic, that's still ongoing, there have been a lot more usage of online tool and technology. And it was estimated that last year, 3 trillion minutes were spent on Zoom globally, which is equivalent to 5.5 million years. With the amount of internet traffic that's increasing, there's also a lot more data being shared across and powered. And that has a cost in terms of electricity and energy consumption as well. It's actually estimated that the digital and ICT sector may contribute between 1% and 6% of global emission, with a forecast estimating that by 2030, this may exceed 20% of global energy used. For now, the increase in energy consumption related to ICT has not materialized, thanks mostly to efficiency in hardware. There was a very good report published last December by the Royal Society that showed that despite increase in energy consumption associated to ICT, digital technology, from smart meter to supercomputers, weather modeling, and AI, could actually help delivering 1/3 of the carbon emission reduction required by 2030. And it's this idea of optimizing the use of bigger and richer data set and harnessing more efficient hardware and data infrastructure as a way to reach net zero that is kind of the theme for this workshop. We are lucky today to have 3 experts that will present different aspects of developing and adapting algorithms and models to make better use of more powerful hardware and the availability of richer and bigger data sets. I'm now going to hand over to our first speaker, Chris Maynard, who is Associate Professor of Computer Science at the University of Reading, as well as expert scientific software engineer at the Met Office. And he's going to tell us all about how to train your supercomputer. Over to you, Chris. I'm going to stop sharing.
Okay, well, thank you, Camille. Thank you for organising the workshop and for giving me this opportunity to speak. So I'm going to try and share my slides. Great. Okay, so the title of my talk is How to Train Your Supercomputer. The Met Office does weather forecasting and also does climate science as well. So, and we produce these forecasts for lots of different customers, which is the general public, but also for the UK military and for the emergency services and planners and things like this. So we do a lot of forecasting, and in order to do that numerical weather forecasting and the climate modeling, we run the codes that do those do those calculations on a supercomputer. So I'll tell you a little bit more about that supercomputer, and in particular the fact that power constraints and the end of Moore's law are radically changing what it is we have to do in order to exploit these machines. So really, we're looking at the end of the free lunch. Now you may be thinking, there was a free lunch. Did I miss it? Well, yes, there was a free lunch, and that was in the past. When you bought a new computer, it was faster, and so your computer program would run faster on this new computer simply by the fact you just bought a newer processor. But that's no longer true. So we'll look a little bit about why that is, and in particular why these supercomputers are now getting so enormously huge and how much power they consume. So this is a picture of the Met Office supercomputer. It's 36 cabinets of something called a Cray XE40 with Intel Broadwell processors in it, and there's quite a lot of them. So there's more than 6,000 nodes, which is about 250,000 processors in there. 250,000 cores. And here's a picture of the power supply. It's 3 megawatts, and that's a lot of electricity in order to power that many processors. And why does the machine have to be so big and consume so much power? Well, so the Met Office is in the game of predicting the future. This is a plot from Intel about predicting the future, and it's actually predicting the end of the world. It's a plot from Intel from the year 2000, and it shows that the problem that they're going to have from the year 2005 in keeping the temperature of the silicon down if they kept doing the same thing. So basically, the power density would get too high at junctions to keep the temperature low, and so the temperature in silicon would increase to past a rocket nozzle. And in fact, silicon actually melts between the temperature of a nuclear reactor and a rocket nozzle. So that's probably not the right thing to do. And so the problem is you can't, you can still make your circuits smaller in silicon, but you can't turn down the current and still get the circuit to switch. And so you end up putting more electricity into a smaller and smaller area. So that increases the power density and increases the temperature. And so you can't keep doing that. So instead of doing that, you end up with more silicon with more switches in, but you can't run it faster. And if you want to build a supercomputer out of these things, then you've got a massive power problem. And so this is a picture of an American computer scientist called Peter Kogi. He's receiving an award for the best paper at International Supercomputing 2015 for his paper updating the energy model of future exascale systems. And basically the premise of the paper is can we get to an exaflop, which is 1 billion floating point operations per second, using CPUs for less than 20 megawatts? And the answer is no, you can't. And there's sort of a twist asking for some more power, and you can't really have any more because you've just used it all. So instead of doing it with CPUs, we're going to have to look at using different sorts of processors that may increase the number of flops, but will do so in a more power efficient manner. For example, using GPUs. So here's a picture of a supercomputer called Summit, which was the fastest supercomputer in the world up until recently, and as you can see, there's a huge number of cabinets there and a huge number of GPUs in that machine. And so basically the problem is we still have Moore's law in some sense continues, though it does appear to be slowing down, that we can double the number of transistors every 18 months, but we can't increase the clock frequency anymore because of power constraints. And this has been true since 2005. So since 2005, we have not had a faster computer. So we have more computers, not faster computers, and that's we have a global power problem because the supercomputer now consumes more power. And so not only that does it consume more power, but we have these very highly parallel machines. Parallel computing is quite difficult to do. So in fact, there's a quote from Seymour Cray, which is, "Which would you rather plow a field with 2 strong oxen or 1,024 chickens?" So here's my 2 strong oxen, and here's my 1,024 chickens. And as you can see, that's a lot of chickens. Now, those of you who are good at counting will notice that's an 8 cubes, so that's 512. So actually, I need another one. And that's a lot of parallelism. So the difference between programming the thing in the middle, where I've got 2-way parallelism, to 1,024-way parallelism is much harder. And we're already at the stage where the Met Office supercomputer already has a 250,000 processors, not just 1,000. So this is becoming quite a challenge. And not only that, we have to think about how we actually do the calculation. So in terms of how fast can you compute something, I like to think of it as a computational sausage machine. Now, you might say, yes, Chris, that's just because you're obsessed with sausages, and that might be true. But the point is that it's a good model for computation. So how fast you can compute something really depends on 2 things: how fast you can turn that handle, that's the processor speed. Well, now the processors can get faster, so we have more sausage machines instead of faster sausage machines, and how fast you can pour stuff into the top. So how fast you can access the data in memory, and that determines your output speed of calculation. And if I'm doing things in parallel in a distributed memory machine, then I might have some remote data to do as well. So how fast I can do that remote communication also becomes an issue. So those are the things that control how fast I can do pretty much any kind of scientific calculation. But not only have we got to do things in parallel, but we've also got a memory problem as well. So this is a plot from the 2007 DARPA X-Scale report, and it shows the relative speeds of memory access to CPU cycle time. And as you can see, whilst memory in fact has the red line, the memory has got a little bit faster over time. The processor speeds were getting much faster, and now they don't get faster anymore, but now we have multiple processors instead. That's the blue line, and so the amount of time it takes to get data out of memory to feed that processor is proportionally longer than it was before. And you can look at that in terms of energy cost of data movement. This is taken from a paper by Kester et al. And it looks at the relative costs of doing the floating point operation and then compared to moving stuff around in memory. And the bottom line is that the data movement costs 2 orders of magnitude more energy than actually doing the floating point operation in the first place. So the data movement is the thing that's really inflating these energy costs. So if you're thinking about optimization, how do we write a computer program that can do this, could cope with this amount of parallelism? Then we have to think about optimization. Now, we have to think about the processors as well. So modern processors have active power management. They manage the clock speed. The clock speed might go up and down. They might individual units within the processor might do things at different speeds. They might power off actual units within the processor. You may even power down individual cores. And so how much energy a processor takes depends on what it's doing, which is the active power management. But for the Met Office, the time to solution is the critical factor. So, for example, we run a 171-hour global forecaster that runs twice a day, and it's got to be done in less than an hour of wall clock time. In order to get those forecasts out to our customers, we have to do it in less than an hour. So we use the processors optimally for time to solution. So we don't recode our software to use less energy, but we might we are adapting our algorithms and software to use more power efficient processors, and that means more parallelism. And when we've done that, we will use those optimally for the time to solution, but we're trying to reduce the total power consumption by using more power efficient processors. So that's quite a slightly different emphasis on sustainability. So how much energy does it take to do a forecast? Well, most of we can actually measure the electricity consumption of an individual model run, but typically the processes are kind of on anyway. And so whilst the power consumption does very little bit, it doesn't actually change that much, basically, if the computer is on. So a very simple calculation then is just to look at the power consumption for the whole machine, and then look at how long it runs to take a forecast, and look at how many nodes we might use. So to do a global NWP forecast, numerical weather prediction, like produce the picture in the background there, do that forecast for 171 hours, 1 week, takes 1 hour. It might run on something like 500 nodes. We do that twice daily. We do it with multiple ensembles, so multiple starting positions, and also do data examination, etc. So it's not just that, but to do the deterministic forecast just on its own will take about 250 kilowatt hours. Well, how much energy is that? Well, we could look at household appliances in comparison. So here's a microwave oven. Other microwave oven brands are available. So yeah, a microwave oven, it's of order 1 kilowatt, but you might run it for order 1 minute, so that's about a 60th of a kilowatt. So heating something up in the microwave oven is way less than an NWP forecast. What about, say, a refrigerator? So, okay, depending on how big it is, for about something that's about 2/3 of a meter cubed, that might take about 50 kilowatt hours per month. So that's per month, as opposed to 250 kilowatt hours per forecast. Electric heater probably take order of magnitude more than that, than a refrigerator, to heat up your hot water if it's an electric water heater. But again, that's per month. So now that gives us some kind of rough idea. We go for the other extreme when we could look at transport. So the Eurostar train, for example, has a power rating of 16 megawatts. It takes about 2 hours roughly to go from London to Paris when we could travel on the Eurostar train. So that's of order 30 megawatts. So that gives you some idea about how much energy compared to other things doing an NWP forecast. So it's certainly quite a lot, but it's nowhere near as much as transport. Okay, so unfortunately I can't actually see a clock with my slides, so I don't know how long I'm taking here, which is probably bad. So I've just stopped.
You have another about 15 minutes.
Sorry, say again?
You probably have another 15, 20 minutes.
Okay, great. Right. So the Met Office has just finished a procurement for a new supercomputer. This is going to run for supercomputing vision for 10 years. We're looking for a big increase in capacity, factor of 6, and then in the first 5 years, and then another further factor of 3 to 18 times our current capacity in the second half. And in order to try and reduce the power consumption, at least 50% of this new capability can be located, at most 50% can be located outside the UK in order to look at sustainable electricity powering of this new supercomputer. Okay, there's a few other things there, but it's an eye-wateringly large number. That's more than £1 billion worth of supercomputer that we're procuring. The procurement's all finished. We've got it's all been agreed and signed off, but it has not been announced yet, so I can't tell you who it is and what the machine will be. In fact, I don't even know. So that hopefully will be announced in the next couple of weeks. But the point is, in order to try and make this huge power consumption sustainable, up to 50% can be located outside the UK, where we might have access to either a more sustainable or cheaper or less carbon footprint power supply. So I've probably got too many slides, so I'm just going to quickly skip through these ones. So Lewis Fry Richardson was the first person to try and ever do an NWP weather calculation, and so we're calling the new weather model that we're developing for the reasons described just mentioned after Lewis Fry Richardson, called ELFRIC. And so one of the things we're trying to do is we're replacing the very successful Met Office Unified model, which does both climate and weather and climate, with a new model which has a different dynamical core, where we maintain the accuracy but improve the scalability and the ability to exploit other programming models. So we did have something that the model was on a long lat grid, that's a structured mesh. We're moving to something that doesn't have the poles, and it's the poles that create the problem for scalability, because you end up having much more communication around those poles as the grid cells get very, very close together. So we've completely changed the model in order to avoid that problem.
I have done 2 minutes. I'm not sure if you change your slide, but I'm still seeing the one about funding approvalology.
Okay, so hopefully you can now see a slide that says a programming model.
Yeah, now I can see it anyway, so hopefully
Okay, good, thank you. Sorry about that. So the slide did show this. It said basically we're changing the way we discretize the problem on the grid in order to improve scalability, and that's a big change in the model because we've had to change the mathematics completely. Having done that, we can then think about how we write the software, which is really what I'm going to talk to you about. So we need a programming model. So we're writing in Fortran, which is a high-level language. We've all heard of Fortran, right? Okay, so it's an abstraction of the numerical mathematics, and the implementation and architecture is hidden. The code, of which we see an example on the right, is just some text which conforms to the semantics and syntax of the language definition. And then we have a compiler which transforms the code into machine code for specific processes. And this is a very nice separation of concerns, and it means that we can have performance and portable code. And this is the separation of concerns between the abstraction, which is the numerical mathematics, and the implementation, which is the about the actual machine architecture. However, this abstraction is broken by all the parallel and performance and memory features that are exposed in order to make the machine program run fast, and then we have to hack them back together. And we have a zoo of different things: MPI, OpenMP, OpenACC, OpenCL, CUDA, partition global address space languages, SIMD, compiler directives. There's new things like Cocos and Cyclone. And these are libraries, they're languages, they're language extensions, they're directives, they're compiler-specific directives. So, this is horrible. At the top is the nice programming model I wanted when I chose a high-level programming language like Fortran, but here's the one I've actually got on the bottom. And not only that, I don't know what happens when I switch one of those dials to 3 and turn a flicker switch on or off for a different programming model. The programming models don't know anything about each other. This is horrible. This is not a nice way to program. So we're making our own domain-specific language. So why? Well, there's too many programming models. There's a rapid evolution of diverse hardware, and the parallel and optimization code is polluting the science code, and so it makes it very difficult to write single source science code. So we need to try and restore this separation of concerns, which we do with a layered software architecture. And so we have basically a domain-specific language embedded in Fortran, and we're using the Fortran 2003 object-oriented coding style in order to control that API. If we do that, we then can use a Python application called Cyclone, which can parse and transform and generate the parallelization system layer code, which is shown here on the left. And that has its own intermediate representation. Okay, so Cyclone itself is developed mostly by the Hartree Centre, but has contributions from people at the Met Office and from the Australian Bureau of Meteorology. The key to making this all work is, in fact, is to be domain specific, and the fact that when we write a kernel, we already know more about what that kernel is going to do than you can express in the standard language in terms of the arguments that are passed in. So we actually write this because we know what it is. We actually write it down, and that means that the code generator Cyclone can read this information, this metadata that we see here at the top, that tells what it's going to do. It's going to read a field, it's going to increment it, and it doesn't matter what space it's on. So we can specifically write this information down, and that means that the code generator can then make choices about parallelism and optimization in order to do the exploit parallelism across the horizontal looping. So this is for a matrix vector kernel. Here's the actual code that does the computation itself, which looks like pretty much Fortran 90, and all the parallelism is automatically generated. So then we can do things like we can then play with different programming models, and for example, we can generate both OpenMP and MPI, or in fact both. So if we had a degree of freedom that was living on a shared entity, which is, for example, an edge, and this was partitioned, so we have some data which is owned by one processor and some data which is owned by another, then they would receive a contribution from both the owned and the halo cell. So we can choose, for example, to do redundant computation into the halo for the shared DOF, and that means we then don't have to communicate that information, so we have less communication. If we choose to do that, and we do it with MPI only, Now, for example, if we had 4 MPI ranks, they all have halos, and that's shown on the left. Whereas in the hybrid version, with one bigger MPI task has a bigger halo, but there is 4 OpenMP threads that share the work across that halo. And so the boundary to area scaling means there's literally less work for the OpenMP threads to do, which is what we can see here. This is the scaling of the matrix vector. If I do redundant computation, and this is for a fully populated node, and on the left it's pure MPI, and as we move towards the right, I'm increasing the number of OpenMP threads and decreasing the number of MPI ranks. And as you can see, the matrix vector starts to go faster as I have less work to do with more threads. I can go further than that, but I'm going to run out of time with reducing computation, so I'm just going to skip through the next slides because otherwise I'll run out of time. So here we can see some what the actual generated code looks like. So here we have a halo exchange that's been generated, and we call basically down through our various libraries to MPI, but the code's realized it's got to do a halo, that it needs the halos to be updated before it can do the calculation, so it calls a halo exchange. So we can do various transformations whereby if we do more redundant computation, which is what we see here, we can then see that, so here we see some more redundant computation. Then we can reduce the number of halo exchanges because that data has been computed on multiple processors, so we don't have to do the halo exchange. Okay, and that results in a big reduction in the number of halo exchanges. So we can also look at changing the algorithms we use. So this is using a multi-grid solver, and so we compute on different grids, and in order to use a preconditioner. So the solver itself uses a geometric multigrid, and if we have OpenMP and MPI, that gives us a bit more flexibility. But basically, for this particular scaling run, so this looks at a 9-kilometer resolution model for a particular test that we're doing. It's on the Met Office supercomputer. I can compare 3 different solvers, so multigrid as the preconditioner, and then a BiCG stab solve, and then a BiCG stab to a higher tolerance, 10 to the minus 6. I can look at the performance of those things. If I can run between 384 nodes and 3,000 nodes, so that's up to 124,000 cores. As you can see, the local volume gets rapidly smaller as I scale out. So this is the performance. You can see the performance then. So the top panel shows the relative cost of the Krylov subspace solvers compared to multigrid. And as you can see, multigrid is much faster, and the parallel efficiencies on the bottom. So perfect scaling is 1. So you can see that the multigrid, which is the pale blue with no hatching, shows much better scaling, scales much better closer to 1 with parallel efficiency because it's doing less communication. So that means on the top panel, when we get out to many more nodes, the Krylov subspace solvers are having to do more communication, so they're much slower. So the relative benefit of doing multigrid gets bigger as we scale out further. We can look at that in terms of the communication costs. So here's the top panel shows the halo exchanges, which is basically MPI send and receive, and that's bandwidth bound. So as we scale out, we in fact see that the amount of time spent in halo exchanges gets less, which may be slightly counterintuitive, but the boundary itself is also getting smaller, as well as the ratio of the comms compute changing. So as we go to extreme scaling, the local volume gets much smaller, and so whilst the actual amount of halo exchanges times takes less, the relative cost, because the compute takes much faster because that's scaling with the square, whereas the boundary is scaling linearly. So whilst we see that the halo exchange cost is reducing, it's actually relatively increasing compared to the cost of computation. The bottom grid shows the bottom panel shows the cost of doing the global sums, which we need to do in a Krylov subspace solve, and you can see that for multigrid, the cost is massively reduced. You see quite a lot of variation because it's latency bound, and Aries network on the Cray supercomputer has an adaptive network to take account of other traffic in the machine. So you see a large variation in that latency. But the multigrid is way faster because it's doing way less communication. We can also look at how we try and use accelerators, like, for example, GPUs, in this new model. So we can also generate open ACC with Cyclone. We're exploring this for the Elfric model. We have problems with compilers actually getting them to compile the Fortran, so we're working our way through those. But the tests for single kernels work well. We're also testing kernels using the OpenMP 4.5 style offload, so we can choose different programming models to target different hardware. We can go further than that as well. We can look at more exotic things like field programmable gate arrays. In principle, we could either target other programming models like Cocos and Sickle, and try and use as much of this rich domain-specific information we capture in the domain-specific language and then we use in the internal representation of Cyclone. And we're progressing this further. We have a collaboration with the US Air Force who use some of the Met Office models and Oak Ridge National Laboratory. We're exploring code refactor and optimization for physical prioritization codes for CPUs and GPUs, and using other domain-specific compilers like the Claw compiler. So the final thing I wanted to go through very quickly before I run out of time is thinking about different precisions. So computers use floating point arithmetic. It's not exact. It has variable accuracy compared to real numbers, and it's not associative. This can lead to accumulated round-off error. And the more precision we use, the bigger the data type is. So we might try and hide this lack of associativity and accumulated round-off error by using data types that have a higher precision. But that's bigger data. That's more data to move around the machine. So in the case of the Met Office and the Met Office codes, we have a semi-implicit time-stepping scheme. And the solver is part of a larger nonlinear system solution procedure. And the accuracy of that solve is dictated by the stability of the time-stepping scheme itself. And so there's various constraints on that, but once the solver error is sufficiently small, it's the discretization errors that are dominating the accuracy of the solve. And so once you reach that point, increasing the accuracy of the solver does not increase the accuracy of the final output. So you get to a point where there's no point in solving. You've done a good enough job. Now, actually, we're solving a matrix vector system, so it's AX equals B, where A is a large sparse matrix that basically encodes the PDEs that we're solving, and it's a very large matrix. It's of order a few hundred million, basically. So it's a very large matrix distributed across a parallel machine. B contains the forcing terms, the initial conditions that we're going to solve from. So there is something called the residual vector, which is defined here. R is the norm of R is the norm of AX minus B, where X is the ith iterate solution. This is called the residual. And we stop when that's less than some small number. Now, given the statement below about the limits of the accuracy of the solver, when that residual is reduced by 3 or 4 orders of magnitude, so 10 to the minus 2 or 10 to the minus 4, we've reached that limit. We've already saturated that solve, so there's no point in going any further. But of course, that's way bigger than the precision limits of 32-bit. And so solving in 64-bit does not increase the accuracy of the solve whatsoever. So we can try and use a 32-bit solver. So this is then comparing for an idealized solver, comparing 32-bit, 64-bit, and 128-bit arithmetic. As you can see, they all start together, but after a little while, they do diverge. The 32-bit takes more iterations for the residual to fall to some required level, and so we have an iteration gap, as it were, between the different precision solvers, but it does still ultimately converge. We can try and account for that by measuring the loss of orthogonality in the Krylov subspace, which we can do by pretending the 128-bit arithmetic is truth and comparing that to the 64-bit and the 32-bit. And what we can see here is some orthogonality measure here. So we're losing orthogonality in the Krylov subspace as we go along. And we can see that in red is the 32-bit and in yellow is the 64-bit. And you can see that the red diverges from 0 and tends towards 1 faster than the yellow does. So that means the 32-bit is losing orthogonality faster than the 64-bit. So there is some loss of accuracy. But for the Met Office, because of the solver only needs to be done to the 10 to the minus 3 or 10 to the minus 4, we don't really see that having a big effect, and so we get the benefit of solving in single precision, which is what I'm going to show you here. So this shows you the actual model, not just the idealized solver, and you can see the bottom line is that basically mixed precision is twice as fast because the data can move in and out of memory, in particular in and out of cache. You can double the amount of cache you use if I use single precision. So we can start looking at mixed precision codes. So some conclusions then. So it's actually the breakdown of Dennard scaling has had a radical impact on process design. There are no faster computers in electronic silicon. It's the end of the world, and that happened in 2005, and there's not been a faster computer since then. We've only had bigger computers that are more parallel. And parallelism, as I've tried to describe, is quite hard to do. So we've had to redesign our algorithms. So with this gung-ho dynamical core, we've had to completely change our discretization and change the mesh. We're looking at communication reduced algorithms, doing redundant computation. So we've had to completely redesign our algorithmic approach to solving these problems. Doing so, we've also had to redesign our software, how we write it. There are many programming models for diverse computer architectures. So if we want to really exploit them, we have to really change about how we think about our software. In order to get that performance portability, we've had to try and restore the separation of concerns. And so hand coding everything really has stopped being an option for us. And we're also having to rethink our ideas about accuracy and precision. There's a typo there, sorry. And we really have to, in order to do that, we need to think carefully about what our uncertainty and errors mean, so we understand the accuracy, so we can think about what precision can we calculate in. And all these things require a close collaboration between science domain specialists, applied mathematicians, and computational scientists. So I'm going to stop there. Thank you for listening. For further information, there are a few papers on some of the things I've just talked about. Thank you.
Thank you very much, Chris. That was very interesting. So if people have questions, please put them in the chat. There should be time at the end for Chris to ask anything. I'm happy to take one question now, if we have time before Parter's talk. I have one from Jill. Do you have a feel for how much of the improvement of weather forecasting is due to better hardware versus programming versus mathematical model or better data?
Yeah, that's a really good question. And it's kind of it's a balance between all of those things. I mean, better and more data has a massive impact. So the increased accuracy of the starting point makes a big difference. So the better we know the starting conditions, then the way better the forecast is. If we can exploit a bigger computer because they're not faster anymore, then we can increase the accuracy because we can increase the resolution, or we can put more complexity into the model. But to do that, we have to be able to exploit their computers. So we need better programming and a better mathematical model in order to be able to exploit these new computers. So some of those things kind of all depend on each other. So it's a bit difficult to kind of tease them out, if that makes sense. You could run the same model and just run it at, for example, at higher resolution, just to see what the effect is of getting like using more hardware. And so yes, that does have a big effect. But in order to exploit some of these new machines, we have to do better mathematics and better programming as well.
To add on to that, one of the questions I have is the move towards the cloud and more parallel computer and more computers. What's the impact in terms of the cost of moving all the data that's being generated as well across those computers? Because as you said at the start, one of the biggest costs is in moving data more than doing the computation themselves. So how do you balance that?
Yeah, absolutely. So with this new procurement, we may be moving much more, moving things much more off premises. So then it's what is the cost of the data? Where does that data live, and how much does it cost, and how does it cost to move it? So typically for large data sets, you want to try and move the compute to the data rather than the other way around, because it's just too expensive in terms of time and energy and cost to move the data. So that's certainly going to be a big change with this new new system that we have, but seeing as I don't know what it is yet, I can't really answer that question. Unfortunately, I was hoping we'd be able to give you much more information. I was hoping we would be able to tell you now, and I would know, but unfortunately, I don't. So yes, that will be something that's something that will change quite a lot.
That's brilliant. Thank you, Chris. I have one question from Edmund, but I might keep it for at the end to just let Partha give his talk in case.
Sure.
That's all right.
Thank you.
Hopefully, he will be able to hold on to the end of the different talks, and he can answer his question.
Okay.
So Partha is joining us, and he's going to give us a bit more of a view in terms of using your hardware and designing our hardware to take advantage for when you design your machine learning algorithm. So Partha, over to you.
Yeah. Just to check, can you see my slides and the scribbling?
Yes,
Okay.
I can. Thank you.
Right. So I'll be talking about a very specific thing, and I think the last talk gave a very good context. In particular, the Q&A and the last question kind of is a starting point of my talk, really. And I have been thinking, how do I spend 25 minutes talking about various way you could accelerate your ML algorithms? And then I thought, maybe there is one thing we can focus on, and we understand how that one thing can help to improve all the algorithms you try to do. And it's a kind of common theme in if you look at supercomputers or mobile computers or cloud computers. Now, to constrain a little bit, I'll be talking about inference because I come from ARM, and where we do a lot of mobile computing, where we run models for inference. For example, computer vision applications, speech processing application, where you deploy them for smartphones or IoT devices, and we do a lot of inference and we optimize models. So I'll be talking about three things mostly. So Chris talked about two things: precision, sparsity in your algorithm, and then he also talked about 1024 chickens, which is Kramer's code. And the question is, if you have many cores, like 1000 core, how do you program them? And then you have your memory bottleneck. So there is a metric actually you can look at, and that is called arithmetic or compute intensity. And you can do clever tricks with your algorithm to make sure that your cores, like if you have 1000 core in your machine, that all of the cores are utilized properly. Because if you want to make it more efficient, you have to make sure that all your cores in your platforms are utilized properly. If they are not being utilized properly, you're wasting energy. So we'll talk about what is this arithmetic compute intensity, and then we'll talk about how to make use of that metric while you are doing performance tuning, or even while you're coming up with a new algorithm. And we'll study a case for convolutional neural network, because this is something is very popular and widely used in these days in many various applications, particularly in vision and speech. So before I go on to in detail stuff, I want to give you an overview of a system on chip or hardware. And if you look at supercomputer, it might be slightly different, but more or less you'll see the main components still do exist. So let's say you have your smartphone where you have a camera sensors where data comes in, and you have a central interface, and then your data goes into the bus, and then it goes back to some kind of image signal processors. And once you do some kind of pre-processing, data goes back to this DRAM. And then you will have some kind of convolutional neural network accelerator. It could be a CPU, it could be an NPU, TPU, GPU. Basically, the CNN engine pulls data from DRAM and do some computations here and send the result back. So this part is the most sensitive and important part. So we will focus on this particular section. So if you look at any accelerator, vector accelerator, if you generalize, or any neural processing unit, you have two parts. You have this big box, and this is your compute engine, and you have your main memory, which is your DDR main memory. And within your big compute engine, you will have some SRAM sitting here, and these are on-chip memory, where you take your data. Let's say you have to do convolution on activation. So you load your parameters here, and you will have a activation buffer, which is also another SRAM, and you will have your activation sitting here. And in your compute engine, you basically have to inject all these parameters and these activations, and you do various dot products, right? And all these PE or processing elements, you do many dot products, maybe 500, maybe 1,000, maybe 2,000, maybe more. And then you do some, you get your result, then you do some kind of nonlinear activations, then it goes to output buffer, and it goes back to main memory, which is DRAM. And sometimes you might reuse some of the activations to do computations on top of them. And two metrics are very important is the bandwidth here from DRAM to main compute engine, and we measured that using byte per second. And the other metric, which is very important, is operation per second, meaning how many operations per second this processing element or this compute array can process. Now, as you can imagine, that you have to have a balance between the byte per second, the traffic coming in from off-chip DRAM, and the amount of compute you can do on your given hardware. And if you don't balance that out, either you will starve these processing elements, meaning that your utilization will not be high as 100%, maybe it will stuck in 60%, 70%, or it might happen that you have a problem with the bandwidth in the sense that you don't have enough traffic coming in to make use of all the processing elements. And the way we combine these two metrics, byte per second and ops per second, is something called compute intensity. We often also call this arithmetic intensity, and this is called ops per byte. And this comes from byte per second divided by ops per second. Okay, and understanding this compute intensity, arithmetic intensity of your platform and your algorithm is very, very important. So let's look at how do we define this compute intensity of a hardware. So there is a plot called roofline model. So this is called a roofline model, and this is often used in when you're doing performance tuning, either in hardware or in algorithm. And on the y-axis, we plot gigaops per second or ops per second, which is your compute power. And here on the slanted line, we plot the memory bandwidth, which is gigabyte per second. And on the x-axis, what we plot is ops per byte, which is the compute intensity. And the roof, the horizontal part is the computational roof, and you have this slanted part, which I call it memory bandwidth roof. And given a hardware, you will have you can characterize, and you can look at the spec and you can find out what is the limit of a given processes. Now, this is a theoretical limit. In reality, you have other constraints with the technology and how things works, and you might have a ceiling, and we'll come to that. So now, any algorithm, anything you plot here, let's say you plot something here, or you plot something here, I can divide this space with this vertical line. So anything on the right, which any algorithm goes on the right, they are computational bound in the sense that they are limited by amount of compute or processing element available on the hardware. And any algorithm falls on the left are actually constrained or are bounded by memory bandwidth, in the sense that it might happen that you have a lot of processing element, but because your memory bandwidth is not enough, you're not able to pull enough data. Now, as I said, that in a realistic scenario, your roof is a theoretical number, but in real, after somebody sell you a silicon, a chip, you might have a different number, and that number will be lower than that. And in fact, that we call it computational ceiling. Okay, and here we call it memory bandwidth ceiling. So that will be slightly lower than what's advertised. And then what we do is you can take an algorithm and look at a part of the algorithm or the whole algorithm and compute it ops per byte. and then you plot them on this graph. So let's say you have an algorithm 1, and that falls here. You have an algorithm 2 that falls here, and your arithmetic intensity or compute intensity is defined by your algorithm, how much parallelism you can actually exploit. It's kind of defined by this number. Now, given this, let's think about how to make use of this metric. So many algorithms, if you look at, you will see that certain algorithms are compute bound. For example, this algorithm P2. So here we are looking at convolution layer in a CNN. So if you imagine a CNN will have many convolution layer, and then you will have some fully connected layer, which is like a multi-layer perceptron. And this part is actually compute bound. So this is P2. And if you look at this fully connected part, that's this P1 part, which is actually memory bound. So not only one algorithm itself either is compute bound or memory bound, part of it might be compute bound, part of it might be memory bound. And it is important to understand and analyze that such that you could modify your algorithm the way you compute to make it more efficient. Now, you have to remember that this roofline model is different for different platform. So for example, you have in blue color is TPU, which is from Google Neural Network Accelerator. You have K80, so NVIDIA, and Haswell from Intel. And if you look at the roofline model, that every hardware, their memory limit and the peak compute limits are different, right? So as a result, even if you look at the same algorithm, let's say this is your algorithm, you're trying to accelerate that on, let's say in a Haswell processor, you are limited by compute. If you put on a TPU, you are actually limited by memory. And this is very important to look at. And not only your hardware has a different roofline model, your algorithm, so there are various types of deep neural network, they have a different arithmetic intensity. For example, if you look at this particular model, which is CNN1, it has a very high arithmetic intensity. If you look at here, over 1,000 mac ops per weight byte. That if you look at an algorithm, let's say MLP0, which is more like a fully connected layer, your arithmetic intensity is very, very low. As a result, if you try to accelerate these two algorithms, your strategy would be very, very different. So it's worth looking at your algorithm and your hardware and how they interact in that space. So how do you tune then an ML algorithm? Let's think about an example. In most of the systems, actually, in today's world, as you can imagine from what you learned from talk from Chris, that memory is a big challenge, memory bandwidth. And more or less, they are restricted by the amount of traffic you can pull in from main memory to your compute core. And let's say you have an algorithm which you designed, and that has the arithmetic intensity, which is here. And if you try to improve this algorithm, want to improve the performance, you want to increase the gigaops per second, right? You want to improve the ops per second. But unfortunately here, as you can see that even if you improve your ops per second, you are not going to improve the performance because you cannot pull in any more traffic, any more relevant data to do any more compute. So basically you are running out of reuse of your data, which is on your SRAM or on chip. So one thing you could do, you could try to improve the arithmetic intensity of that algorithm, right? So let's say you improve your ops per byte in your algorithm in some manner, such that your arithmetic intensity gone up. And then if you try to increase your ops per second, then you are now not bottlenecked by memory, but rather you are bottlenecked by this computational ceiling. At this point in time, basically you cannot do anything, right? You might have to choose a different hardware maybe. And if like company like us, we have to think about how do we improve the computational roof by putting more processing element. So it could happen for you as an algorithmic designer, you choose a different hardware. In that scenario, let's say you increase your computational roof to somewhere here. and let's say your memory bandwidth hasn't changed in your platform, and then if you increase your ops per second, you are again hit by memory bandwidth, right? So you went step 1 here, A0 to A1, and then you went from A1 to, let's say, A3. And so you converted your problem from a compute bound to memory bound. So now you cannot do anything anymore, right? So only thing you can do now, again, improve your arithmetic intensity. That means you have to improve your ops per byte, and you might come here and then you increase your ops per second, then you are again limited by your compute limit. And if you want to improve more, you have only one option, is to try another platform. So this is the way, step by step, you actually want to tune your algorithm. And I'm giving example here in terms of convolutional neural network, but this could be applicable to any algorithm you're looking at, any machine learning algorithm where data reuse is very much possible. Now, I want to, so we have around 10 minutes. So I want to do a case study on CNN to emphasize how we do it on a CNN, for example. So just to be familiar with the CNN, in CNN, you have your input image or input activations, and then you go through alternative convolution and pooling layers. So these are the blue ones, the pooling layers. And question is, if you have to design a convolutional neural network, how do you design this layer such that it's efficient? And if you look at literature today, the way Google, Microsoft, or Facebook and going on, there are so many different type of convolution layers available, right? And not all of them are actually useful, in the sense they are not efficient. Although if you go from, say, 2012 to 2017 or 2018, you will see that the spatial convolution are replaced by this one-by-one convolution, then they are replaced by depth-wise or group convolution, and etc. And what you want to do is to calculate and fill up this table. And this table, basically, you can summarize your arithmetic or compute intensity. So CI here is for compute intensity. And you can calculate the number of ops and amount of memory required for a particular layer of operation. And you could look at a full model, but let's say we're looking at a layer level granularity. And then you look at compute intensity, and you can compare all these different types of convolution, and you can see that it makes sense or not given your platform. Okay, so to give an example, let me go through a spatial convolution. If you're not familiar, let me give you an highlight. So what happens here, you have an input tensor, and the tensor has input images, right? And you have many such input images, right? So you have X by X input images, and you have M number of input images. And let's say we call them activation for the time being, okay? And then you apply a different filter, right? So let's say you have a red filter, you apply M red filter. So this is M because you have M channels, M red filters on this input tensors, and then you get this red output channel or output activations, right? And you will have many output activations or output feature maps or output channels, and there are, let's say there are n of those. So you have to have n different filter set to do these computations, right? So if you have to compute intensity, we need to compute how many ops are required and how many bytes or memory you need to do the operations on. So let's say you have to compute this number of operations. How do you compute? Actually, it's very simple. You have this input image, which is x squared. Each of the input image will be convolved with w square element, right? And you have m input channels and n output channels. So you have x squared times mn operations to be done, divided by, you want to know how much memory you need. So for memory, you have to load this activation, and these parameters, right? And it's simple to count again. You have this particular activation, you have x squared times m, because you have height and width, x and m channels. So x squared m. You have similar number of computations, memory here, activations here. You have x squared times n, and you have filters. You have w squared m filter for one, and then you have n of those, right? This is w squared mn. So if you sum them up, you get this number here, x square m plus n plus w square mn. And if you compute this, if you use a realistic number, so for example, here we are using spatial convolution of 3 by 3, number of channels 5 and 2. This is a generic number. You could look at a particular model and then you get this number and you can then fill up this table, right? So in spatial convolution case, we filled up with number of operations, 462 million. You have number of your memory ops, number of memories or million memories 2.56, and you can divide, you get a computational intensity of 180, right? And we normalize these to 1.0. Now let's go back and look at one more, just to make the point. So there is another convolution which became popular recently. It's called one-by-one convolution, and its strange name. It's basically you, instead of having W by W filter, you actually have one-by-one filter, meaning you have one element basically, and you have one element for each of the channel. And now, if you calculate your compute intensity here, you basically have to make W is equal to 1, and you get this number. Okay, as simple as that. And similarly, you can do it for group convolution, where you have different groups of convolution, and here you divide by G actually. And you have other convolutions like depth-wise convolution, which is very, very popular at the moment, and you get a different compute intensity. And I did this study, and here we now summarize. And when you summarize, you can see that main objective in the research community was to reduce number of flops, that is number of operations. And we did, right? From 462 million to 0.9 million, we improved quite a lot. But actually, does it improve your performance? The answer is not really, because your memory required to do these operations also has gone down significantly. So 2 million, 2.5 million to 0.205 million. When you calculate your compute intensity or arithmetic intensity is 4.3. And if you normalize, you can see that it's 1 and here it's 0.02. As a result, you actually reduce your arithmetic intensity or compute intensity of your algorithm. Is this a good thing? This is not a good thing, because you are thinking that you reduce your number of operations, but in reality, what you did, you created a bottleneck in your algorithm which cannot be accelerated. So basically on this graph, on this roofline model, your spatial convolution, maybe you were sitting here and it was bounded by computational limit, like amount of processing element or number of cores available. Now you shifted that problem to this region where your arithmetic intensity is very low. As a result, your algorithm is memory bound. Your performance deteriorated quite a lot. So this is very, very important, that on a high level, you might think that reducing number of operations will improve your model performance, your inference or training performance. In reality, that is not the case. You really have to look at this inherent metric called arithmetic or compute intensity. Now, I want to mention with that another pitfalls which often we hear is that people often say, oh, we took a model, we designed a new model, we have 4x less operations to be done, floating point operations or integer operations, whatever it may be. So one of the things people do in convolution world is they use FFT or Szmaragd. If you're doing signal processing, this you are familiar with this. But the main idea is that if you have input activations, you do some kind of transformation to input activations, and then you get an intermediate representation of your activations. Similar thing you do with your parameters, you do a transformation, and then you have an intermediate representation of your parameters or your weights. And then you do element-wise dot product instead of convolution. You get an intermediate output, and then you do an inverse transformation, and you get your original result back. The advantage of doing this kind of algorithm, this kind of implementation, is that you reduce your op count by significant amount. So say, for example, Szmaragd will give you easily 2x improvement. 4x is possible. Even some of the algorithm, variant of the algorithm will give you 6x, but 6x only you will get on theory. When you try to implement, you are actually hit by the problem of compute intensity. So basically, by reducing your ops count, let's say your ops by byte, that's your compute intensity, you reduce your op count, but your byte is kind of constant. So as a result, your intensity has dropped. And as again, you you moved the problem from compute bound to a memory bound problem, right? So you have to be careful about about this intricacy in how the model is being run on a hardware. The same story with one-by-one convolution, depth-wise separable convolution, and these are all modern techniques we are quite often we are using to improve our model performance, but in reality, they really don't improve. And sometimes this could be mitigated by exploiting some other model of data parallelism, but it's not always possible. So it's better to be careful. Another thing, we have 2 minutes, so I'll just mention one more thing, is when you are trying to deploy or tune your model, your performance of your model for any particular application, you have to look at something called power envelope and the power budget, right? So if you look at these dots are different machine actually, and different machine from different applications, target application, and if I cluster them, these points are platforms which are data centers. For example, GPUs, high-end CPUs, etc. You have your big CPUs, something like an ARM A class, and you have microcontrollers, something like ARM M class. And then in between you have accelerators like DSP accelerator, which comes from say Qualcomm or companies like CEVA, and you have accelerator which is like, let's say, TPU or NPUs. These are coming out, and as you can see that their power envelope is different. Their gigaops per watt is different. As a result, their arithmetic intensity requirement will be different in the sense that how much memory bandwidth they have, how much compute limit they have is very different. And you want to be sure that you understand that very well. So to give you a concrete example here, you have different processors. So you have high-end NVIDIA processors where they are expensive, very power hungry in the sense that they are power efficient, but overall TDP is very high because their throughput is very high. So their compute throughput is 13 teraflops per second, for example, a lot of memory, to something like a microbit, our microcontroller, where it goes for IoT applications. Your ops per second is very small, your memory is very small, your power budget is 1 milliwatt compared to say 250 watt, and it's cheaper because it's IoT devices. And as you can see, if you are the strategy you are applying to optimize your model to be applicable to NVIDIA GPU may not be applicable to an ARM MCU or let's say a smartphone like Google Pixel. And this is something to keep in mind. So we are just on time. So I just want to summarize what I talked about is that if you want to make your model very efficient, energy efficient, and make most use of your multi-core machines or many-core machines where you want to make sure your core utilization is high, is not only first thing you want to reduce your model size, that will improve your memory footprint, you want to reduce your ops count at the same time. Actually, the best way to do is to look at this part. That is, you have to balance your memory and ops footprint. Not only reduce your model and ops count, but you want to reduce this ratio of ops divided by byte. And if you do that, and if you look at your roofline model, probably you'll be doing better than just trying to reduce, say, model size. And the other thing is you also have to look at other data reuse, like can you load something from main memory to your compute engine? So if your DRAM compute engine, and can you make use of all the data before you throw them out? And that is very important to improve data reuse. And the last but not the least, and the most important point actually, is you have to find bottleneck in your model architecture and improve. Your main total model may not tell you much of the story. You have to look at individual atomic component of your model. Say, for example, in CNN, it's a layer. And not all layers and all functionality of your model will be well suited to your target hardware. And you have to tune your model individually to individual layer to get the best out of it. With that, thank you very much for listening. And I'd be happy to answer if you have any question.
Thank you. And my point of view is you kind of try
Actually, your voice is breaking. Can you repeat? 1 second, I didn't get anything.
Oh, sorry. I was going to say, from as a statistician, often you try to reduce the number of operations when you're thinking about an algorithm taking too long. And it's very interesting to see that trying to reduce number of operations in your algorithm might not necessarily solve your problem. So thank you very much for kind of showing this balance between your memory and your ops footprint. I think from my point of view, is definitely a take home I'm going to take going forward.
Oh, that's great. Yeah, yeah.
Do I have any question for Pata in the chat? I don't see any at the moment. I might ask one if that's okay with you.
Sure.
When you're designing an algorithm, so I think you mentioned about looking at every single layers. Do you have any advice for statisticians and data scientists that might know their algorithm from the statistical point of view, but not necessarily understand the computational aspect and where to look?
Yeah, so I think one of the thing in statistics, so we are looking at Bayesian neural network, for example, which are kind of sampling-based model. So one of the problem with sampling-based model, for example, in statistics is you have to draw a lot of samples. And when you try to do a lot of samples in our world, it's like we are doing many inference on the same model to get a much more better estimate such that your variance is very low. And in doing so, you are running the same model many times. Is there a trade-off you could play with where you might be able to get enough confidence of your prediction of your sampling by drawing less number of samples? In that sense that you will spend less time in doing this sampling part. And this is one of the problem we are facing at the moment. We are trying Bayesian neural network, and of course you have to do something like a variational inference or something similar where you have a sampling involved. And we are trying to fit one forward pass or one inference or one sample on our embedded hardware at the moment. We are struggling with that. And now all this emerging algorithm like Bayesian, you have to do, let's say 10 or 10 plus forward pass or inference or sampling on the same hardware. And that is not possible. So is there any trade-off you could play with such that you could get the same confidence level in your model by doing less number of inference or drawing less number of samples?
So it's almost advising to rethink our models, how we go about drawing the samples, or the all underneath models.
Yeah.
That's very interesting, Pata. Thank you very much.
Thank you very much.
So I'm going to now invite our last speaker, Jacob Tomlinson, to kind of follow on from Pata's talk, because he's going to talk to us about GPU from the NVIDIA maybe perspective.
Sure. Let me share my screen. Right, I'm going to assume that everybody can see my screen. Please shout if you can. But yeah, I'm gonna go through a talk today and talk about a project that I work on NVIDIA called Rapids, which is a suite of tools for doing data science workflows accelerated on the GPU. So a little bit about me. My name is Jacob Tomlinson. I work for NVIDIA. Specifically, I contribute to Rapids and Dask. They're both open source Python projects. And I mainly focus on kind of deployment and scaling and kind of getting stuff running on various clusters. So that can vary from the cloud to local workstations to HPCs, supercomputers. Now, why are we talking about GPUs in terms of data science? Well, GPUs provide quite a lot of general purpose compute performance. You can fit a whole load of GPUs into a single machine. You can interconnect them tightly using things like NVLink and NVSwitch to get really high throughput in terms of memory transfer between the devices. You can scale up this to add a load of more like servers to build up supercomputers. I think as Chris showed in his talk, Summit, which was one of the largest supercomputers in the world, is a GPU-based machine. Now, given that the theme of this, we're talking about some sustainability, I just wanted to share some numbers from some data benchmarking that we do, where we're comparing 6 NVIDIA DGX A100 machines with 19 Dell kind of equivalent machines running like the same kind of benchmark, one using CPU, one using GPU. Again, I think in the last talk kind of talked about how NVIDIA cards use a lot of power, but then give a lot of performance. So in this example, running through the same benchmark with 6 NVIDIA systems, we'll use probably around twice the power of using 20 Dell servers, but it'll execute that in much less time. So the actual overall usage of the cards is much lower. which means when you're scaling out, when you're speccing out large systems, you just buy fewer of them, right? And get bigger utilization through your machine. So what I'm going to do kind of through the rest of this talk is talk about what we're doing within Rapids and how we're trying to change folks' workflows to enable that kind of acceleration that I kind of showed in this slide, right? Taking a benchmark down from 16,000 seconds to 600 seconds is a nice change for running the same kind of workflows. This is kind of end-to-end loading in some data, doing some natural language processing, doing some machine learning, kind of standard big data queries that you would run in like a data science workflow. So what we do within Rapids to give that kind of acceleration is we focus on like the whole end-to-end data science stack, right? So from loading in some data, cleaning it up, doing preparation, through to training models of various different complexities, right? Whether you're using something like Cyclone or whether you're using neural networks, machine learning, deep learning kind of technologies, and then all the way through to the visualization of giving the output to the end. If we can accelerate all the parts of this, we can get these kind of performance benefits. Rapids is open source. It's all up on GitHub. You can head to our Rapids organization on GitHub and find all of the libraries I'm going to talk about here. You can contribute. You can fork it. You can do whatever you like with this stuff. This is all open source software, and it's worked on by a bunch of people. So although this effort is kind of coordinated by NVIDIA as kind of the hardware manufacturer, what we care about here is people making use of this hardware. And so it's a big community. There's lots of people contributing to the software, building pieces of it. We have folks kind of using it, like publicly talking about what workloads they're accelerating with it. And this is all part of a larger kind of open source ecosystem, right? So this is part of the PyData kind of ecosystem. So just to kind of revisit these benchmarks again, we have this standard benchmark that we call GPU BDB. You can go and find it on our GitHub. It has all the benchmarks kind of written out in Python. And we use that to benchmark each various systems. There's a few examples here of comparing using some DGX1 systems, which are a few years old now, compared to using like much newer DGX A100 systems. Kind of each time we get a new iteration of hardware, we tweak the software and tend to get more performance out of it. So, comparing different stages of a data science workflow, you might have your load and preparation step where you're reading in some CSV files or something and doing joins and transformations and maybe splitting out variables into separate columns and all that kind of stuff. Then you might pass it through some machine learning algorithm. Maybe you're doing some gradient boosting on some decision trees with XGBoost, and then you probably want to visualize some outputs. Here's some comparisons of running on various CPUs compared to GPUs at the bottom. So to talk about what Rapids actually is, let's kind of go through the core of the framework. So this is an overview of the kind of familiar PyData ecosystem. If you've used any of the PyData tools, some of these names should be familiar to you. So when you're doing your kind of data preparation, your data analytics, maybe you're using pandas to load in tables of data, maybe you're using NumPy to load in arrays and ND arrays of data. If you want to do some various like statistical operations, you might use scikit-learn. If you're doing network analysis, graph analytics, you might use NetworkX. And then as you move on to the deep learning, there's a bunch of libraries out there, right? PyTorch, TensorFlow, all that kind of stuff. And then visualizations, you've got Matplotlib and like HoloViews and Bokeh and Plotly and all those kind of things, right? This is the kind of current ecosystem. Some of these, like PyTorch and TensorFlow, have accelerated themselves using GPUs and have kind of CPU and GPU flavors. But much of this full workflow is heavily run on the CPU with kind of small parts of it dipping into GPU acceleration. What Rapids is here to do is to provide kind of equivalent libraries. So like one of the core concepts here is the Python libraries that are part of Rapids feel like a one-to-one comparison to the non-GPU accelerated versions, right? So for doing like loading in data frames and doing data frame analytics, instead of using pandas, you would use QDF. The Python API is exactly the same. You import a different library, but you use it the same way. It has all the same function calls, takes all the same inputs. But the idea is that it's just the code is executed on the GPU instead of the CPU and provides you some acceleration. The same, we have QML, which is kind of an equivalent to scikit-learn. We have QGraph, which is an equivalent to NetworkX. We still use PyTorch, TensorFlow. Those are great libraries. We just contribute to those and make sure that the interoperability with the other packages is there. And then a bunch of the visualization libraries are also now GPU accelerated. And all of this uses Apache Arrow as like an in-memory format for storing data in RAM, which allows us to transfer from one library to another without having to do any copying in memory. Allows us to get that kind of data reuse without moving stuff from the CPU to the GPU and back again frequently. So the software stack for Rapids, although we have Python at the top, in order to get the performance that we want, we're writing things in CUDA, which is NVIDIA's like programming paradigm for general purpose GPU computing. Built on top of that, then there's a whole bunch of CUDA libraries to kind of abstract out a bunch of things. You have Thrust and Cub and things like that. Then on top of that, we tend to build C++ libraries. So each of the different things I showed you before, QDF and QML and things tend to have like a C++ implementation built on top of CUDA. And then we go through a Python layer to expose the Python API. So from a Python developer's point of view, you come along, you install the package, you use the package like you would any other, but it's calling down into like C++ CUDA code. But it shouldn't feel any different to using a pure Python package. So I'm going to walk through some of these different packages in a little bit more detail, just to talk about kind of what they're targeted at and how they're kind of accelerating on the GPU. So QDF is like one of the core staples of Rapids. It's used by like the majority of our users. The idea here is that it's just like pandas. You read in data frames, you read in tabular data from a varying different formats. You can kind of do all this kind of standard stuff you would do with pandas, but all of that kind of operation is accelerated on the GPU. One of the like big benefits to this is actually reading in data. Like lots of data formats are generally inefficient, and so reading in something like a CSV file, right? Lots and lots of folks work in CSV files, which is funny. Right before I worked at NVIDIA, I worked with Chris at the Met Office, and was used to working in optimized file formats. And then you come and see some other use case, and all the data is stored in CSV or JSON or some other format. So GPUs can actually be really useful in just reading in string data. Like they're not historically haven't been very well known for handling string data, but there's a library called QStrings which enables a whole bunch of parallelized string operations. So reading in these file formats like CSV is now extremely performant on GPUs. Now comparing using pandas to using QDF. If you read in a bunch of data, maybe you want to merge some tables, maybe you want to sort, maybe you want to do some group by operations. We've benchmarked those in being kind of hundreds of times faster running on the GPU compared to their CPU equivalents. Yeah, my slides are slightly out of order. So yeah, this is kind of what I was saying about reading in different file formats. Pandas supports reading in and writing a whole bunch of different file formats. QDF also supports those and aims to accelerate them by doing more efficient things. Like, in Python gives you a whole bunch of benefits in terms of like a programming model. You don't have to worry about types so much and all that kind of thing. But it means, and some file formats also don't care about that. You have a CSV file, it doesn't care about types. It has no data about types, and Python doesn't. Python needs some types, but you as a developer don't need to care about that. So in order to read in a CSV file into a pandas data frame, you have to do a whole bunch of type inferencing to work out what is this column and how do I get it into the right structure in memory. And it turns out that kind of operation is really well parallelizable on a GPU. So being able to do that in QDF instead allows us to read CSV files and write CSV files extremely fast, as well as more optimized and performant file formats like Parquet. But ETL is I'm talking about this whole extract, transform, load kind of workflow within data science. But this goes beyond data frames, right? It's a very common use case, but lots of folks also care about array computing. People will use NumPy traditionally, but there's a whole bunch of different array representations. Each of these different libraries, right? If you've used PyTorch or if you've used TensorFlow, they have their own representation of an array, which is just equivalent to like a C array in memory. But they all kind of have their own abstraction of that array object. So one of the big things that Rapids has done within the community is to work on various interfaces to allow you to convert from one library to another without actually modifying the data in memory, right? You have your data array on your GPU, and you've read it in with, PyTorch. Maybe you want to switch over and do some operations in CuPy. You can just cast one object to another in Python, and that, because we've got this nice interface, it does like a zero copy transform and just points to the same memory addresses. And thanks to CUDA array interface and DLPack, we can now kind of swap between a whole different range of packages. So if you traditionally use NumPy, you can switch over and use CuPy. The API feels the same, but you can then, when you've done some work in CuPy on your data, you could then switch over to using PyTorch or TensorFlow without having to kind of dump out the memory and reload it. So you get a whole bunch of optimizations there that are just gone within this paradigm. So one of the ways that we deal with this is GPUs also have a few kind of constraints compared to doing CPU computing. One of them is around memory management. Operating systems typically will handle a lot of memory management for you and deal with paging things in and out of memory. GPUs kind of don't have that level of sophistication in terms of handling memory. So one of the things that we do within Rapids is we use a library called Dask that I'll talk about a little bit more, which kind of handles the memory paging and swapping things in and out, among other things, right? But one of Dask's use cases is parallelizing out a workflow and doing out-of-core operations. So it handles where chunks of memory go. So we can, within a scalable workflow, if we have a large array of data, we can load that in pieces, right? So on a CPU, you would load that in like NumPy chunks that kind of represent a much larger array, which allows you to do larger than memory operations. And you can move that onto the GPU by using CuPy arrays instead of NumPy arrays, and everything works exactly the same. And again, doing some benchmarks on running array type workloads with CuPy versus NumPy, doing an SVD or something like that is going to be more performant on the GPU. Now, all of this, like these benchmarks weren't necessarily looked like this before Rapids existed. This is kind of like a coordinated community effort to come in and work on accelerating these things so that these kind of workflows are fast on the GPU. So I think a slide back here just kind of mentioned number. I'm going to take a very small detour into number just because I think this is an interesting topic. If you are interested in GPU computing and how you can do it in Python, I've only got a couple of slides on this, and then I'll kind of switch back to Rapids again. But number is a Python library that you can use to write code to execute directly on your GPU. It kind of abstracts the CUDA programming model. So you literally, you conda install or pip install number, and then from that you import CUDA, and you have a whole bunch of CUDA tools within that. And you can work with arrays in whatever type. So maybe we're going to work with some NumPy arrays in here. So this first slide is just showing I'm going to create an empty array of zeros with NumPy. This is just happening on the CPU. This is just using NumPy. I'm going to make an 8x8 array of zeros. This is going to create, an array in memory, like main memory. And then my next line of code, I'm going to move that array down onto the GPU. Now, this is something you tend to have to worry about in this programming model is kind of which memory am I using, because I've got two different sets of memory. So we'll create an array full of zeros and we'll move it down onto the GPU. And then in Python, I can write a function. I'm going to kind of, let's read this from the bottom up. So I'm going to call a function and I'm going to give it this array. But because we're executing on the GPU, we can do this in parallel, right? We can call this function, but have this function execute many times in parallel. And we can specify the kind of shape of that, the thread model, right? So we're going to say, I want this to execute in an 8x8 shape. So we'll get 64 threads running on our GPU. I'm specifying this in 2 dimensions. You can specify up to 3 dimensions. Generally, this is just useful if you're trying to fit your problem to your how your execution is running. But say here, I'm going to run 8x8 threads. I'm going to have 64 threads. And each one of those is going to take a pointer to this array in GPU memory. So we have the function above that, which we've decorated in Python with cuda.jit. This is saying, this is a Python function, but please JIT this function using number CUDA, which this means is it will run this function through LLVM and actually compile it down to GPU bytecode at runtime. So the first time you call this function, there's like a very small compilation step, but then every time you call the function after that, it is cached the bytecode there. So we can call this function. It takes in the array. When we run this, this function will be called 64 times at the same time, and they'll all have this pointer to this same array. And we want all of these functions to operate on this same array, but we need to make sure that they're not going to tread on each other's toes. So what we can do is we can use CUDA to say, what is my thread index? Which thread am I of the 64? You know, if I'm the first thread, I'll have an index of 0, and if I'm the second thread, I'll have an index of 1, you know, with a 0 counted index. So we're going to take that into the variable position, pos. And then what we're going to do is we're going to update one element in our array. So just the element in the array that corresponds to our thread index, we're going to update just with the value of our thread index. So this means that we're going to call this function 64 times. Each execution of that function is going to change one number in that array. We call this, everything happens in parallel. And then if we have a look, we copy the data back onto the CPU so we can have a look at it. We can see each thread has placed its index into that array. And everything's been updated in parallel. And I think, like, sometimes I personally, when I first joined NVIDIA a couple of years ago, found it hard to get my head around how you can write GPU code in Python. And this is kind of one of the simplest examples I could come up with. So if you found that interesting, I actually I gave a talk in the autumn about how to do GPU development in Python. It's up on YouTube from a local tech conference in Exeter. Go and check that out if you're interested in more of that. But I'm going to kind of switch back to the higher level stuff in Rapids. So another library in Rapids is QML. This is the scikit-learn equivalent. So if you've used scikit-learn in Python, QML has a bunch of the same tools and the same utilities. So say you're doing something like some cluster analysis, you can use dbscan to you know, find some clusters. This is some kind of scikit-learn code where we're going to make some moons, convert them into a pandas data frame, and then we're going to use dbscan to fit our two clusters and plot them out. If you want to do this in a GPU accelerated way, it's just a case of swapping out the imports. So instead of pandas, we're going to import QDF and create a QDF data frame. And then instead of importing scikit-learn, we can import QML. We're actually still using the make moons function from scikit-learn here. Everything's kind of compatible with each other. But the idea here is that the code looks pretty much the same, using a slightly different library, but everything is running faster because this algorithm has been accelerated in C++ by some members of Rapids to run on the GPU. So within QML, there's a whole bunch of different algorithms which have been accelerated. These are all things that have been, you know, implemented, that are currently implemented in scikit-learn, that have been re-implemented as part of QML and part of Rapids. So you can use all of these on the GPU. And then just some more benchmarks. This presentation is very heavy in benchmarks. I apologize, but it's just kind of showing the various performance speedups of those different operations by executing those on the GPU. There's a bunch of other libraries that are slightly more domain specific. I'm going to kind of go through those a little bit faster, but these are generally built on top of the tools that we've discussed already or well integrated with them. We have QSpatial, which is a geospatial library. Is frequently used for doing things like, I have a large data set which is full of points, and I need to calculate all of the have-assigned distances between all of the points for whatever algorithm I'm running. And so that's the kind of operation which is very nicely parallelized on the GPU. That's been implemented in QSpatial for you, so you can take a data frame of points and run a parallelized performant have-assigned function on that. There's a whole bunch of different algorithms that have been implemented for working with geospatial data. There's also cuGraph, which is an equivalent to NetworkX. So if you have a large graph of data, maybe it's web pages, maybe it's something else, cuGraph allows you to do a whole bunch of different algorithms. Again, these have been re-implemented in C++ using CUDA and then exposed via the same Python APIs as NetworkX does. So if you want to run PageRank, or if you want to do a breadth first search or something through a graph, you can do that in an accelerated way without having to learn a new tool if you're already familiar with NetworkX. And then lastly of these, there's QSignal, which is a signal processing library. And again, it does the same kind of thing. I think QSignal is the one outlier within all of these libraries in that there isn't a C++ layer. Everything here has been implemented in pure Python, but jitterfied with number, right? So everything in this library is just using number to write some pure Python, but then compile that code at runtime down to execute on the GPU. So all of this stuff is GPU accelerated, but it's just written in Python, which there's trade-offs to whether you're going to do stuff in C++ and expose it as to whether you're going to write stuff with number and JIT compile it. And so a lot of it's around, a lot of the trade-offs are around learning curves. And like this is an easier project to get into if you're interested in how number works. And the last topic I'm just going to come back around to is Dask. Now, this is actually the project that I spend the bulk of my time working on. And Dask is kind of shown in the Rapids diagram as this kind of layer sat across the top of these other technologies. The idea behind Dask is it's a cluster management tool. You deploy, it's a single scheduler module, right? So you run a scheduler on your cluster, and you have a bunch of workers that also run. You can deploy it with various HPC systems. You can make use of MPI. So you might run a scheduler on rank 0 and then workers on all your other ranks, and they'll all connect together. You can run on the cloud. It's kind of got all this built-in deployment tooling that feels very native to use within Python. It's got the same kind of abstractions that Rapids does, in that if you're used to using NumPy, you can use Dask array. If you're used to using QDF and pandas, data frame kind of libraries, you can use Dask data frame. It's got the same kind of APIs, they feel the same, but the idea behind Dask is that it is doing stuff in chunks. It's building up a computation graph of whatever your code you're writing, and then executing it in an out of core chunked kind of way. So you can do operations which are larger than memory. You can do stuff distributed on multiple machines, and Dask will handle the communication between all of the workers. So Dask also supports various communication protocols. So by default, Dask workers will communicate via TCP, but also we have support for UCX, which allows us to tap into InfiniBand or NVLink or shared memory, and get some various performance boosts by doing so. So Rapids allows you to take what you know with the PyData ecosystem and kind of accelerate that and scale that up with the GPU to run your various algorithms faster. And then you can mix that with Dask to then scale out onto multiple nodes, multiple machines on the CPU, or multiple GPUs, or multiple nodes with multiple GPUs in terms of Rapids. And everything's kind of, because all of this is fitting into interfaces within the PyData ecosystem, and also kind of copying the same APIs, all of this stuff is kind of cross-compatible to the point where NumPy explicitly supports things that are like NumPy and allows you to kind of dispatch to lower functions, but I won't dip too much into that. There's a bunch of other folks out there that are building on top of Rapids. So although these are kind of low-level tools for use within data science and science workflows, there are other people out there building kind of more specific, like community-specific tooling. So within Rapids, we have a project called Clicks, which is targeted at the InfoSec community. So folks that are processing lots and lots of logs, looking for unusual activity, unusual traffic. Clicks uses natural language processing to inspect logs. Typically, if you want to do like if you're looking for unusual log messages, you end up doing all sorts of things with regular expressions and kind of slightly gnarly stuff within InfoSec. But by using these tools, it kind of exposes you to the whole machine learning world as well. So you can use more advanced algorithms like BERT, like as a language model. If you're kind of interested in that, there's a whole bunch of stuff about BERT and SciBERT on the Clicks repo. A lot of the groups within the PyData ecosystem, there's kind of like a sub-community within PyData called PyViz, which covers a bunch of different plotting libraries, whether it's data shader for doing kind of oversampled plots, where maybe you have lots and lots of data and you're trying to show, I think this is some census data in this picture here, maybe using bokeh to do kind of web-based plotting, or using HoloViews to do interactive plotting. A lot of these libraries have either of their own accord or with help from Rapids written interoperability with Rapids in order to use GPUs to accelerate the plotting as well. So say you have some data that you've loaded in, maybe you've loaded in the US census data or something. You can do all your operations on it in QDF, and then you can also plot it in data shader, and everything will execute on the GPU. And the last one here is NVTabular. This is another NVIDIA project, which is a higher level API on top of things like QDF, which allows you to kind of worry more about what you're doing with the data, not necessarily how to store it or scale it, for doing various ETL workflows. So if you're interested in that, go and have a look at NVTabular. And then lastly, we have Blazing SQL, which is a SQL engine built on top of Rapids. So a lot of folks out there want to be able to use SQL to load their data and query it before moving on to some other tool for maybe doing some machine learning or something. And Blazing SQL allows you to load in your data and query it with SQL, but it's calling down into Rapids underneath. So there's no actual SQL engine. It's all kind of converting SQL into Python calls through to Rapids. I'm just going to skip over that one. So if any of this stuff has been of interest to you, you can head over to rapids.ai. There's like an installation page. You can install Rapids with Conda. You can grab the Docker image. These are all Python packages. We use Conda to package them up because there are compiled dependencies that come with it. But you can go and install it there. And then you can try it out wherever you like. Anywhere that you've got an NVIDIA GPU, it's got to be in the last couple of architectures of GPU, but there's a whole bunch of places you can get those. I tend to recommend Blazing SQL notebooks to folks. It's a managed interactive notebook environment. You can go to, I think it's notebooks.blazingsql.com. If you search Blazing notebooks, you'll find it. It gives you an interactive kind of Jupyter notebook experience, but it has a GPU, it has Rapids installed, and you can kind of try out and experiment with this stuff. We're continuing to develop these libraries. We're continuing to engage with the community and build out a whole bunch of things. So it's kind of still early days for what we're doing. But I hope this has been interesting, and I'd be happy to take any questions.
Thank you very much, Jacob. That was definitely very interesting, especially if you're like me and come more from the R roots and don't know so much about Python or Rapids or any of this. It's quite enlightening. So thank you very much.
Sure.
I'm happy to take any question for any of the presenter. I'm just going to mention that Partha unfortunately had to leave us to go to another meeting. But if anyone has a question for Partha and want to put it in the chat, I'll pass it on to him and we'll try to come back to you through the RSS. I had an early question from Edmund for Chris, so I'm just going to ask him now. And if anyone wants to put us a question in the meantime, that'd be brilliant. So Chris, can the same single precision trick you mentioned towards the end can be performed at a lower precision? And if not globally, can you make certain calculation less sensitive? Or is such filtering too difficult?
Yeah, hi. So the short answer is yes. The longer answer is it's slightly more complicated than that. With a Krylov subspace solver, of course, we can be guided by the residual, and we know what we can see all the time what's happening with that residual, so we can monitor the convergence of the algorithm using that residual vector. And in fact, you can do, and there has been plenty of work done in multi-precision solvers, where, for example, if you need to do solve to a particular accuracy, you can in fact do the bulk of the work in lower precision and then pay the cost of a restart. So you do all the work in a lower precision, say 16 or 32, get an answer, and then restart the solver in a higher precision to do a few iterations just to get the answer in the higher precision. So you can certainly play games like that, and a lot of early work was done with playing with mixed precision solvers. So we can certainly look for doing that. The other thing, if we're thinking about multi-grid solvers, we're already using the geometry of the system, using geometry to precondition the system that we're going to solve, and we use geometry to do that. And you can think about doing that at low precision as well. So, and certainly you can think about doing communications in arbitrarily low precision down to 8-bit or something. So there's some other interesting work that's been done by Tim Palmer's group in Oxford, where they use the ECMWF spectral model, and because of the spectral model, you've broken up all the modes into their different spectral frequencies. They actually targeted, using an emulator, different frequency, using the different wave numbers, but use it with different precision. So that was really interesting. So you can look at things like that. So there's plenty of work that could be done that's of interest, looking at doing things at a lower precision than 32-bit. For other things that aren't the solver, we have to work a little bit harder to understand the accuracy. One problem we have, for example, in the is it's quite sensitive to small variations. It's quite branchy, and if a certain value is below some threshold, then trigger something happening. And if we're overly sensitive to that precision, when we don't really know that value very accurately, but in terms of precision we're overly sensitive to it, then that can cause problems. So we have to think a little bit more about how we make our decision making about when triggering events, like is it going to rain or is something going to freeze, a little bit more fuzzy and a bit softer if we want to use lower precision. So yeah, so there are plenty of tricks we can do with lower precision, but we have to think about careful. But the thing we really need at the moment is infrastructure that can cope with mixed precision, so we can make choices about what the precision is for arbitrarily pieces up, like for different components of the model.
Before going to the second question from Edmund, I have one that's kind of applied to both you and Jacob to some extent, which is, what limit do you see in terms of improvement, and would there be a threshold? To kind of give you a bit more context, I'm just thinking a lot of the models that are used now quite currently for machine learning, they're not new model from a statistical point of view. They've been theorized quite to almost 100 years ago, but they were limited for a long time by the lack of data. So we never had enough data to actually use those models, and the lack of computer powers. And obviously nowadays they become quite normal and current, but there are more and more data, and that require more and more precision and more computers, I think, as you mentioned, Chris, in your talk. So what will be the limit, do you think, now, in terms of what can be done, and what would be the limited factor? Is it going to be power? Is it going to be speed? Is it going to be expectation of people in terms of the result?
Yeah, so I think it's a combination of all those things. It's also looking at the whole workflow. So for example, for weather and climate, we take a lot of satellite data that gets fed into a supercomputer. We do loads of calculations, and we have to get data out of the supercomputer and do post-processing calculations on those. And then we have to push that all the way down to, like, whether it's web pages or down to phones. And so there's a data volume and a data velocity problem that if we solve the supercomputer and make it go really fast, we actually make the data volume and data velocity problem worse because the data is coming out quicker. So we have to think about how we optimize the whole workflow. Ultimately, in terms of computing things in using electronic silicon, we will eventually reach a limit of saturating the amount of parallelism, and that comes down from the mathematics of the algorithm. What we're doing for a weather and climate model, we probably have a little way to go before we hit that point. And I think what obviously Jake can comment, but I think what people are starting to do in parallelism in the AI and machine learning using Python probably has quite a way to go in terms of the amount of parallelism they can exploit currently. But eventually, unless we have a new technology that isn't silicon electronics, we won't have a faster computer.
Yeah, I think definitely there's a lot of low-hanging fruit still within the data science community and the Python community in terms of implementing these things. I think something we're finding within Rapids is, like, some algorithms just inherently don't parallelize, and that's kind of a limiting factor. Some things we're finding you can parallelize on hardware that's extremely tightly coupled, like a single GPU. You could parallelize within the threads of that GPU, but then when you start thinking about the latencies involved in going to multi-GPU, the algorithm doesn't make sense, and so we just have to make a decision about, we're not going to even attempt to implement that algorithm for multi-GPU workloads, and those are some limiting factors. But I think, given some of the libraries I was talking about, like something like NetworkX for doing graph analytics, is currently implemented. That is the primary Python library for doing network analytics. It's written in pure Python at the moment. It's kind of very inefficient from like a computational point of view. It's just it's just more advanced in terms of the mathematics. So there's a lot of room to go in terms of optimizing these things and making them more parallelizable. But I think in terms of actual computation, where we're starting to hit bottlenecks with running stuff is now in I/O. We can't get data fast enough onto the chips to do things, which is why we're looking at, there's technologies coming out like GPU direct storage, where you can read from an SSD that's attached to a PCI lane. You can read from that directly into GPU memory instead of having to go via the CPU to try and get some performance benefits there, because we're kind of in some workloads just struggling to saturate the GPU at that point. So yeah, I think I/O is going to be like the next big challenge for rapids type workloads for sure.
Yeah, I think that's true to a certain extent for many science workloads, including the science workload at the Met Office. I had a quote from Seymour Cray, so I should give you a quote from Ken Kennedy, who's a computer science. So what is a supercomputer? It's a device that turns a compute-bound problem into an I/O problem.
That's really interesting. Thank you. Another question from Edmund, which I think was directed to you, Chris, but Jacob might also have some view on that, is about developing a eCO2 budget or value in terms of accounting for data movement work and other aspects, obviously, I think on the compute or visualization or the different workflow to estimate the energy or the E-value in terms of CO2 emission. Is that something that could be done or would be interesting in doing?
I think that's actually very hard to do, because modern CPUs do all this active power management, and the clock speed changes depending on what else is happening. And so it's trying to understand how that will happen with some model. For a complex calculation, when you've got billions of instructions in flight, and the modern processors can cope with like literally billions of instructions in flight at the same time. So I think that would be very difficult to do. And ultimately, certainly for something like the Met Office, it is that we look to reduce our power consumption by computing faster. So we can do run the calculation for less wall clock time ultimately on a more power efficient architecture. And there, the simple analysis of just the processors on it. I mean, the processor does vary depending on what it's doing. The power consumption does vary, but actually it's not a huge amount, because it's optimized to not vary a huge amount, because there's temperature constraints and it operates best with certain things. So actually the time to completion is probably the best way of doing that. And then you've got some simple model which I kind of showed you a few things, like how much does it cost energy in terms to compute a weather forecast compared to running a microwave or something. So I think whilst that would be interesting in many ways, I think it'd actually be really difficult to do.
Edmund, you just posted another question. I just wonder if you would like to unmute yourself and elaborate on your question to all.
Yeah, thanks. Thanks all. It's just from the trying to go from the sustainable computing sort of title, where I'm pushing with these, to some of the aspects. And it just seems to me that until you get a metric which can calculate the thing holistically, it's very hard to. You can optimize the parts, but you can't really see whether you are truly driving down the overall picture. And so, sorry, that's kind of the scene, the kind of the context for some of these questions. So one of the ones was, Chris, picking up on that point you just made on the energy consumption difference being small between basically a computer that's on and effectively idling and one which is off and computing. And it was really interesting seeing the last two talks on the efficiency one. And it just makes me wonder, in a kind of sort of, I guess, in a supercomputer case, but also in a cloud case, what happens if the tasks to compute ever run out? I don't know if that's ever a problem that we face, but you've made this thing super efficient, but can you then kind of effectively reduce your final power output by getting the your CPUs, whether in your supercomputer, in your cloud or whatever, to just turn off and stop consuming when we've run out of tasks, basically? Very naive, sorry.
I guess in principle you could do that, but in some ways the cloud providers sort of do, in the sense that your jobs that are running in the cloud, when they run out of parallelism, they stop and you don't have access to those machines anymore. They're then given to someone else. So whilst they don't actually power down, you're not then using them anymore.
I totally see what you mean, but I'm just thinking about in the holistic worldwide sense of, I guess we don't have that insight as we're not cloud providers, but is there a way so that those can be kind of scaled up and down, kind of like a data center can be, turned off for I imagine it can't be turned off easily for 5 seconds while kind of the overall cloud volume has come down. Sorry, it's just thinking of the very big naive question on a very big picture scale.
I mean, I think there's all kind of things that could in principle be done, but in practice is very hard. I mean, you could even think about, okay, let's build a super smart city where all the central heating is actually processors that are available for cloud computing, and then when you want to heat your house, you turn on the tap and computation flows into your house down the network, and all the processors start computing and heats the house up, right? I mean, in principle, yes, but in practice, it's very hard to manage.
Yeah, I would guess. I mean, like Chris said, with AWS or Google Cloud or Azure or something like that, when you're not using CPUs, they still exist, right? Like they're still in those data centers. Hopefully, some other customers come in and pick those up, but they will have their own high points and low points in terms of their load, and they'll have to have spare capacity. I know they do a bunch of work with reprovisioning machines. If different folks want different configurations, machines will shut down, reboot, and come back up with different operating system configurations. In terms of like the partitioning of the hardware, I have no idea whether they leave them off at all at any point. I guess they could in theory, but I'm not sure. But I mean, there are some differences as well, I guess, between commodity hardware or hardware you would give an end user and then like a supercomputer, right? So I have an NVIDIA workstation behind me which has got some GPUs that's kind of targeted at data scientists to have under their desk, or maybe if you work at Pixar and you want to do some animation and rendering and stuff, like that machine will be configured to throttle back the CPU and the GPU, and the performance will drop heavily when the machine is idling, and the power usage will drop heavily. But you don't want to be doing the same kind of thing in servers and in HPC systems, because those processors are throttling back and forth to such extremes. You're just not going to be able to get the same performance out of those that you would by keeping them. I mean, if you look at some the cloud providers, and I don't know, Chris, whether you do this with your HPC, but I know they specifically speak to Intel and take processors with a much narrower like heat tolerance, and then specifically keep the data centers at specific thresholds in order to tune that performance, right? Whereas maybe a machine that you have under your desk has a much broader tolerance of heat, and therefore is probably going to run less efficiently, but you can scale back and use less power.
Yeah, I think that's probably true. I mean, if you have whether it's a supercomputer or whether it's just like racks upon racks of servers, you probably want that operating environment to be as stable as possible. And as you say, if you can narrow it by saying keeping the temperature and the power draw pretty level, you can probably pack more of them in, and actually that is more efficient than powering up and powering down.
Yeah. Okay. Thank you.
I think we're coming to the end of this session. It was really interesting. I think my main take home from a statistical point of view is that often we see a lot of data and we're throwing resources in terms of computing resources to solve an algorithm or a problem I extract. And I don't think we spend enough time to consider the hardware limitation or possibilities that we have in terms of designing our algorithm. So I think all this talk today would at least encourage myself and probably pass the word that we need to think about the bigger picture, what kind of optimization we can make in terms of how we design our system to make them more efficient. I don't know, Chris or Jacob, if you want to add something before I close.
Yeah, I mean, we're being pushed towards parallelism, and it's worth remembering that parallelism is not easy to do. You look at we're building our own system at the Met Office because we have to and we can. Jacob's busy building a system that makes it easier to do parallelism in data science using Python and using the GPUs. But parallelism is hard, and exploiting things like GPUs is hard. I mean, that's not NVIDIA's fault. It's doing things in parallel is harder than doing them in serial. It just is, right? So we have to think about the algorithm much more, and the algorithm has to come first, and the algorithm tells you how to exploit that parallelism, and then we can look at the frameworks that people are writing, whether it's what Jacob's doing or what we're doing at the Met Office, in order to exploit that parallelism. But you have to think about the algorithm them first.
Yeah, I was thinking this before when you had that Cray quote in your slide, Chris. I was thinking, I think what we're building in Rapids is a cow costume for chickens.
Yes.
Right.
Yeah.
That's what we're trying to do. We're trying to give you something that looks familiar and works the way that you expect, but we are still herding chickens.
Yeah, exactly.
Yeah.
That's what we're doing with the domain-specific language of the Met Office. We are trying to cloak our chickens in a cow suit so you can write as, but you have to think about the parallelism to expose it. But then you want to be able to do it in a simpler way.
Yeah, that's a very good way of putting it. Well, thank you both for presenting, and also Partad, who is left. And thank you all for attending. That was very interesting. Thank you for your time.
Okay, thank you, and
Yeah.
thank you for organising the workshop, Camille. It's been a pleasure. Thank you.
Thank you, Chris.
Okay, bye.